How about now? Is it better? Yes. All right. Again, like I said, very glad to be here. A couple of things before we get started. We took a picture of the group. I want to know if it's okay if I tweet. I'm going to tweet Twitter. So I'm going to tweet a picture just so that the rest of the world knows that we are meeting in Bhopal Sunday. This young boy, before I get started, I want to relate an incident. I was at IIT Kanpur. In one of the offices, there was a notice on in the front. Do all of you understand Hindi?
Yes.
So notice Hindi में लिखा हुआ था. उसपे लिखा हुआ था कृपया आप यहाँ अपना ज्ञान न बांटें. यहाँ के लोग आपसे कहीं अधिक ज्ञान. So there is a ज्ञान course. That's why I said our learning and hope will be together. In fact, there are many people in the audience who are faculty members, very well versed in this subject. I think we will get started. The idea is that if you have any questions, feel free to raise your hands as we go along, or if you prefer to hold your questions till the end, that will be fine as well. So let's get started. The topic is on groundwater and aquifers. Can you all see the screens, or you have the PowerPoint copies in front of you? So groundwater, as is noted over here, is water that's found beneath the Earth's surfaces. It exists in the pores, in the interstices, in the fractures. Usually all of that is called as subsurface water. And then what is called as groundwater is not always consistent, but by and large, water that exists underneath the water table is typically what is referred to as groundwater or groundwater flow. And we will also sort of adopt that kind of a terminology. So all water that's found beneath the Earth's surface, fills pores, cracks, and so on, makes up 30% of all the fresh water. Okay, and the important consideration is that it's a precious resource, needs to be managed very well. We don't do a good job of managing it, not just in India, but in most parts of the world, where we basically draw water without perhaps paying enough attention to what other consequences are going to be. Okay. And we will use the term aquifer very often. Groundwater proceeds, the water bearing formation that we deal with. I think many of you know aqua means water and fere is bear. So aquifer is something that bears water. Aquifers actually serve many functions. The primary ones that we think of are storing and transmitting water. Within the pore spaces, we are able to store vast volumes of water. This is the water that's meeting our drinking water needs in cities, irrigation water, which places a very high demand from the industry also. So it does store water, plus it also serves as a conduit. We are interested in how water moves through these aquifers, through these large areas and large volumes, so that we can essentially move it from where it is to where we need it. Aquifers actually serve as other functions. One is that of a filtering media, and I think you are fairly familiar with it. As water is going to be moving through this porous media, depending on the nature of the surface, we are going to have I was talking about aquifers also serving as a filtering media. Many of you are familiar that sometimes for drinking water, we draw water out of a stream, the surface water. But more often than not, we almost always prefer to basically draw the water a little further away from the stream, from the subsurface, and expect the stream water to have traveled through the subsurface from your intake point, so that we have some benefits of the filtering media idea of subsurface. It also controls base flow, how much water is available in the streams, especially during dry seasons, depends on aquifer properties. And the idea that it is actually a source of water, this is very important, because unfortunately, we treat as if we are mining water. We just keep extracting water, and most aquifers do get replenished with water. But trying to determine what the replenishment amount is, what the replenishment rates are, to basically plan for how much water we can extract, that is not always very simple. We treat it as if it's a renewable source. And indeed, that is true. Water in the large hydrologic cycle, it's just recirculated. But the question is whether it's going to be available. It takes a long time for water to be stored in groundwater. It takes a long time. If our time scale of extraction is usually much, much faster, we are not able to replenish these aquifers rapidly enough for them to be what is called as sustainable. So you hear terms like sustainable yield and optimal yield, which is essentially addressing that question. The other issue that we do have to worry about is the aquifers. We have treated them as if they are a resource that will be available all the time. But like many things, you can extract water up to a certain point, it will still be elastic. Beyond that, it is possible to have very large subsidence, in which case you have lost part of the aquifer also. So we see aquifers as having many functions. The primary ones that we are going to be talking about in this course is to look at storage and how they act as conduits in terms of moving water. Okay. There are several types of aquifers, and we will talk about it. I also wanted to mention that in our talks, we have essentially taken many pictures from the internet. We have tried to source them under the fair use policy. And here is essentially a picture that's been taken from the internet, talks about different kinds of aquifers, and we will define these as we go along. We essentially are looking at a land surface that you see over here with a stream. And we have a couple of aquifers. One is the confined aquifer, which basically is confined in the sense that we have confining layers both on top and the bottom. The confining layers could be completely impervious, or they may allow leakage, but they do allow water to be compressed. Or an unconfined aquifer, where at least on the top it's open to the atmosphere, so we have a water table. And while there might be some compressibility effects, compressibility does not play a major role or plays a less important role for unconfined aquifers. And indeed, if we were to drill wells, which are essentially going to be screened in the confined or the unconfined portion, this is our means of knowing what the piezometric head is or the piezometric surface is at that location in the subsurface water. And then we of course have streams. Streams also interact with the subsurface water. The streams can be gaining streams or losing streams depending on whether water is being recharged to the aquifer or whether the stream is receiving water from the aquifer. Depends on the level of water in the stream and where the water table is or the piezometric surface is in the drowning aquifer. So we'll see some of these terms. Some quick definitions to get us started. Aquifer is a geologic formation that two main purposes: contains water and allows for significant amount of water to be transmitted under typical field conditions. So there are quite a few things that must happen. It has to be able to store water, and you have to be able to move water under field conditions, meaning without having to apply huge amounts of energy. Most of the time, you're hoping that gravity will do most of your work for you. Okay. If you have to expend a lot of energy to put water, then that aquifer is not very useful for us. Okay. There are many examples of such geologic formations: sandstones, conglomerates, fractured limestone, unconsolidated deposits, and so on. Fractured rock is also subsurface media, can move quite a bit of water, but we will not be talking much about fractured rocks because the theory or the principles by which water moves through fractures is different from moving through porous media, and our focus will be on porous media. When we talk about aquiclude, and you'll hear this term, it's a formation that may contain perhaps significant amounts of water, but cannot transmit, water under ordinary field gradients. So unless you do something extraordinary to move the water, it basically acts as like an impervious surface, but it might have a lot of storage. We typically think of tight clay soils, very, very fine pores, a lot of porosity, but not really much help in terms of conduction. Aquifuge is an impervious formation, solid granite. Cannot store water, cannot transmit water. It's a completely impervious surface. Aquitard, what we think of as semi-pervious or semi-confining layers, that's a formation that transmits water, but at a much slower rate than what would be the main aquifer. So aquitards or semi-pervious layers can exist as the bottom or top of aquifers, allow leakage through them, but their conductivities are typically orders of magnitude less than the main aquifer. So the important thing is because their conductivities are less, they are still able to have water be confined and under pressure. So a confined aquifer might have semi-pervious layers both on the top and bottom and still be able to develop pressures. So these are some of the terms that we will be using. The important part, of course, for us is the pore space. This is the portion of the soil or rocks that is not occupied by solid mineral matter. You'll hear many terms: voids, interstices, pores, pore spaces. All of these are synonymous. Because of these pore spaces, that water is either storing water or the aquifer is either storing water or able to conduct water. How these pores are formed, what is the nature of the subsurface media, basically takes a long time to build an aquifer. Like I said, over centuries of deposits, layering, and all that has to occur. And then these interstices or pore spaces, their characteristics are very important in this idea of conduction. What their shapes are going to be and how well they're interconnected. Those are basically important properties. Then there are some classifications that you may see on pores: supercapillary, subcapillary, capillary, and so on. But the idea is that these pores are small enough that capillary forces can become important. In other words, even if the pressure is less than atmospheric, the soil is able to hang on to the water. And that becomes an important consideration, especially when we are talking about unsaturated flows. But the pore space, therefore, their structure, their connectivity, their shape and size, that plays a very important role in subsurface water movement. Distribution of subsurface water, again, just to give you an idea, the top over here is the ground surface. And right next to the ground surface, you will have plants, you will have roots, crops, and so on. There's some biological activity. And then up to a certain depth, typically below the root zone, if you will, we typically call that a soil water zone, but this is not terminology that everybody uses. Then there is a vadal zone, which sort of exists in some sense from the root zone all the way to what would essentially be the top of the water table. If you have very fine pores, because of capillarity, the pores are going to be saturated, but under pressures less than atmospheric, up to a certain height above the water table. If I think of the water table as the location where the pressure is zero, pressure of water is equal to atmospheric pressure, then indeed there is a capillary zone where the soil is completely saturated, but water is under pressures less than atmospheric. And how high or how thick this capillary fringe is will again depend on the nature of the pores. What fraction of the soil has very fine pores versus medium versus large pores. And therefore some of these definitions will tend to be a little, are used loosely in some sense. In many groundwater studies, if we are thinking of an unconfined aquifer, it's not uncommon to think of the top of your unconfined aquifer as being at the top of the capillary fringe. So everything that is saturated, we assume that to be part of the main aquifer. This figure to the right essentially is trying to give you that idea that initially where it's unsaturated, the water content is going to be less than the saturated value. And in the capillary fringe, the water content is actually saturated, and then of course it remains saturated. The pressures below the water table are going to be greater than atmospheric. And if it is unsaturated, if it's unconfined, and if the flow is essentially horizontal, then the pressure will essentially increase in a hydrostatic fashion. but pressures above the water table and certainly above the capillary fringe are going to be less than atmospheric. So we'll have a chance to visit unsaturated flows a little later. Subsurface water, as we said, occurs under subatmospheric or basically negative pressures. Groundwater is what we are going to refer to as that portion of the aquifer that is completely saturated. And if the pore space is being shared by both air and water, even for unsaturated flows for this particular workshop, we will assume that the air phase is not going to be very important in the sense that air everywhere is able to escape to the atmosphere so that it's always atmospheric pressure. And therefore the air space doesn't get compressed and build pressures and so on. What we also assume, as in many studies, is as water is moving through the soil, the frictional resistance that is experienced in the head loss comes primarily because it's rubbing against the sides of the pores. The air phase offers negligible resistance in comparison. The water table, as I said, is going to be a surface through geological formation where at least, let's say that the pressure at all points of which are atmospheric pressure, pre-surface. There is, like I said, there is always a capillary fringe, which in fact in clay soils can have as much as 1 meter or more. But we'll assume that the main aquifer is very thick. Classification of aquifers. So we'll talk about confined aquifers, where, as the name implies, we are expecting that water can be confined and can stay under pressure. Okay, so we need confining layers both on top and on the bottom, sometimes called as pressure aquifers. So both on the roof and the floor of the aquifer, we have to have either impervious formations or at the very least semi-pervious formations for it to behave in a confined fashion. The total head or the energy status of water anywhere, we typically use piezometric head. So pressure head plus elevation head. Velocities in groundwater tend to be much smaller, so the v square over 2g, the velocity head, is rarely a factor in the total head. Within confined aquifers, sometimes you use the term artesian aquifer. So this is also a confined aquifer, but the piezometric surface actually rises above the ground surface. So the water is under high enough pressure that if you were to drill a hole, water would essentially, or drill a well, water would essentially come out and flow on the surface. Okay. So you will see the term artesian aquifer also sometimes used. Unconfined aquifer, also called as water table aquifer or a phreatic aquifer, because the water table surface is sometimes called as a phreatic surface. So unconfined aquifers, that means the top of the aquifer has to be a free surface. That is going to serve as the upper boundary. The capillary fringe, like I said, is often treated as the top of the water table in groundwater studies. If you really wanted to be particular, you could decide what you want to do with it. Then we have leaky aquifers. So both confined and unconfined aquifers could actually be leaky aquifers, depending on the confining layers, whether they're allowing leakage or not. So if it's a confined aquifer, in principle, both the top and the bottom boundaries could be semi-pervious surfaces, and that would allow leakage from both the top and the bottom. For an unconfined aquifer, since it's open to the atmosphere, only at the bottom of the lower portion, you may have a leakage occurring. So both confined and unconfined aquifers could actually be leaky aquifers. So for confined aquifers, now groundwater is confined, it's under pressure. And what this picture then shows you are the confining or the impervious layers in this case. This is the portion of the confined aquifer. If you were to drill a well, water table would rise to a certain height, or the water in the well, would rise to a certain height, which would be an indication of the pressure head, the piezometric head in the main aquifer. And I think one of the things that becomes important to us is if we have a well that is screening the entire thickness of the main aquifer. So the height to which water will rise in that well, what do you think that's going to represent? So, anybody? Pressure, yes. But I guess what I'm leading to is if the well is screening the entire thickness of the aquifer, you're right, the water height in the well, which is a reflection of the pressure head, but that pressure head is somehow being averaged throughout the thickness of the aquifer. In principle, it's possible that the pressure is actually varying in the vertical direction. But if the well is screening the entire thickness of the aquifer, you are essentially, the height to which water is rising is essentially being integrated throughout the thickness of the aquifer. If, on the other hand, the well was only screening a very small portion of the confined aquifer, water was going to be allowed only in that portion, then the height to which water would rise would essentially give you an idea of the piezometric head at that location, not throughout the thickness of the aquifer. This will become important when we talk about groundwater flow. When we say it's essentially two-dimensional flow, we are essentially saying we are using wells which are spreading throughout the aquifer. What we are already measuring is something that is effectively throughout the thickness, and we will focus on horizontal flow. But the height to which water rises in the well, therefore, gives us an estimate of the piezometric head. Yes.
Suppose if it is partially penetrated well,
right,
then the pressure will be different.
Yes.
If it is penetrated totally, the pressure will be different.
The height to which water could rise could be different, depending on what is the nature of flow in the main confined aquifer. If you do not have significant vertical gradients, then the pressure is approximately same throughout. However, if you have vertical gradients, then what you say is right. Depending on what the extent of penetration is, where the well is being screened, that will determine how high water will rise in the well.
Which, whether partially penetrated has more pressure, fully penetrated has more pressure.
I don't know about the more pressure part, but if you are trying to develop the aquifer, you are trying to draw water, let's say from a well. From a partially penetrating well, trying to draw water at a certain rate, you'll expend a lot more energy than if it is penetrating throughout the aquifer. Because you are engaging only a smaller portion of the aquifer and you are trying to draw the same amount of water, you'll have to expend a lot more energy than if it is screened throughout the thickness of the aquifer.
Partial penetration requires more energy.
Yes. Yes. So I think when we talk about essentially horizontal flow, when we use a two-dimensional approximation, we use wells to tell us what the piezometric head, which is driving this horizontal flow. I think that is what I'm sort of leading to with my argument. We say it's analogous to pipe flow in the sense that if you think of water flowing in pipes, which is full and under pressure, then the pipe walls are confining the water and you are able to develop the pressure. Same situation for confined aquifers. So how does water essentially get to the confined aquifer? Obviously, if the boundaries allow leakage, then it's possible for water to enter or perhaps leave the aquifer, depending on the status of the pressure head in the main aquifer, what the piezometric head is on the other sides of these semi-pervious layers. Or, if the aquifer basically, as a geologic formation shape is, if it's going to appear on the ground surface somewhere else, it may be essentially collecting water from recharge at the outcrop. So either of those could be happening to get water into the main aquifer. As I said, an artesian aquifer, which we are trying to show over here, essentially means that the piezometric surface, this is the main, dark blue is the main aquifer, which is artesian. The piezometric surface is over here. So at some points, the piezometric surface is above the groundwater level, above the ground surface. And if you were to drill a well, then water would be able to come out naturally. You wouldn't have to pump it out of the aquifer. And artesian aquifers also would have the same source. Perhaps there is a recharge area where there's an outcrop that the aquifer essentially comes and meets the ground surface, or it has to be recharged through leakage. Unconfined aquifer, as you mentioned, has a water table as a top boundary. On the bottom boundary, you have an impervious layer or a semi-pervious layer. We liken this more to open channel flows, where part of the flow cross section is open to the atmosphere, so we do not think of the flow being heavily pressurized. So same with unconfined aquifers. The top surface is essentially where we think the water table is. We also, like I said, loosely assume that the pressure is zero. This is the unconfined aquifer. Now, unconfined aquifers can be defined simply because of vertical recharge. If you have rain that slowly percolates through the unsaturated zone, joins the groundwater table, replenishes the unconfined aquifer. It can be recharged if you are irrigating, irrigation water. Surface water bodies, for instance, if you have a stream, lateral recharge, it's essentially going to be losing water. If it's in direct contact with the unconfined aquifer and the water table, there's a direct connection. Sometimes it can leach down from the stream, go to the unsaturated zone and join the water table. The mechanisms by which we artificially recharge aquifers to be able to store water for later use, and of course leakage. And then lateral recharge is if it's in direct hydraulic contact with the stream, then depending on the height of water in the stream, depending on the shape of the water table in the adjoining aquifer, the stream could be supplying water to the aquifer, or like I said, we could be losing water, but the aquifer is supplying water to the stream. We also come across the term perched aquifer quite often. A perched aquifer, as the name indicates, it's like a localized unconfined aquifer. So let's say here is the main unconfined aquifer, if you will, where you see a water table, but perhaps in the geologic formation, there is let's say a clay lens, which tends to be less permeable, so that when recharge occurs, basically water is trapped on top of this clay lens. And therefore you have water being held over there as a perched aquifer. And that can also work as a source, but it's not a large source. It's not a big reservoir. So perched aquifers can, also things that you see sometimes. When you have leakage, leakage of course allows, as I said, really allows replenishment of aquifers. So in this case, if this is the main aquifer, and let's say we have over here the top of the aquifer, this is the bottom of the aquifer, and depending on what the piezometric status is within the main aquifer and what the piezometric head is on the other sides of the semi-confined layer, we might have leakage either coming into the main aquifer or leaving the main aquifer. And then we have to basically account for that leakage. So confined aquifer, which is bounded by semi-pervious boundaries that will allow leakage. So these are the aquitars that we talked about. There may exist an unconfined aquifer on top of the semi-pervious unit. So on top of the semi-pervious layer, what we might have is an unconfined aquifer with a separate water table. The water table would indicate the piezometric status of this unconfined portion. And that piezometric head, of course, can be completely different from the piezometric head in the main aquifer. The direction of leakage will depend on the values of the piezometric. And so recharge sources are, vertical leakage recharge from pervious layers, vertical recharge if this confined aquifer is essentially finding the top of the ground surface someplace. Lateral recharge through a stream, typically for confined aquifers, that is unlikely. It may happen, but it's generally unlikely. Same for unconfined aquifers. We can have leakage in unconfined aquifers. Unconfined aquifers are essentially bounded by a semi-pervious layer at the bottom that may allow leakage. Again, the direction of leakage will depend on what is the piezometric head on the other side of the semi-pervious layer versus what it is, within the main aquifer. And the recharge sources are going to be similar to what we have for unconfined aquifers. So with some of these definitions that we are going through quickly, we will also talk a little bit about porous media properties that we are likely to use throughout our, throughout this workshop. One of the fundamental properties that we'll talk about is the idea of porosity. So it's a measure of the relative volume occupied by voids. So if I take a bulk volume of soil, part of the volume is occupied by the solid soil particles. The rest of it is void space. So that can be occupied by water, by air, by any other contaminating fluid. So that's the portion of the voids. And porosity therefore indicates what is the fraction of this bulk volume that is occupied by voids. And as the definition is, if you are going to use a symbol phi for porosity, it's the volume of voids divided by total bulk volume. And so basically this V sub T is the same as V, then total V sub T is the total volume minus the volume of solids, that is space occupied by solid soil particles. So this ratio is porosity. And porosity may be expressed in terms of densities as well. Okay. If you have density, rho sub m is the density of the solid soil particles, rho sub d is the bulk density of the soil, then basically you can use this relationship to find an expression for porosity in terms of bulk density of the soil and the density of the solid soil particles. Okay. Solid soil particles are going to be heavier than water or air, so basically rho sub m is going to be greater than rho sub d, which is the bulk density. As I said, porosity plays a very important role, and we also define something called effective porosity. Effective porosity becomes very important. It refers to the relative volume of interconnected pore space available for fluid flow. So the idea is that even though we have a lot of pore space, some of it is perhaps so fine that it doesn't allow conduction. Sometimes the soil is essentially aggregated in such a way that there is a bulk porosity, but there is also some inter or intragranular porosity, which doesn't really allow water to move very freely. So the effective porosity is that part of the porosity which is going to allow water movement. Okay. So term effective porosity refers to the relative volume of interconnected pore space available for fluid flow. So the effective porosity will be either equal to or less than the total porosity. So either all the pores are conducting or only a fraction of them are conducting. For unconfaulted porous media and for other soil types, sometimes the two porosities are identical and otherwise not. Okay. Porosities may range from near zero to perhaps as much as 50% for soils, okay, depending on the soil material, shape and arrangement of the individual particles, pore sizes, and many other factors. With depth, it's quite likely that porosity will change. Porosity might increase, with depth because of compaction of the overburdened overlying layers, and it is sometimes taken as exponentially decreasing, as given by this particular expression. This table basically shows us some idea of the typical kinds of porosity that we see in soils. As we said, the highest values tend to be around 50%, and you have very low values. I also want to again, low values will be in the order of 10-15%. So it's not just a total porosity. The total porosity tells us the storage capacity. It doesn't directly tell us, it's how much it can conduct. That depends on the size and shape of the pores. But total porosities can range from very low to as much as 50%. I want to talk a little bit, use porosity as an example to talk about the continuum approach. How many of you are familiar with continuum approaches, continuum mechanics? Several of you are. So the idea is this, if I think of porosity is a good property to talk about. Porosity, like we said, we are going to essentially look at a bulk volume of soil and find out in that bulk volume what fraction is occupied by pores. So I'm going to query the soil, and if my probe, when I query the soil, if my volume is so small that this was entirely in the void space, then of course I'll get a porosity of, if it's entirely in the solid soil particle, the porosity will be 0. If I increase the volume a little bit, now I'm going to collect some void spaces and some pores, so I'll get some other value. And as I keep increasing the volume over which I'm making my porosity estimate, it will fluctuate at very small volumes, but essentially I'll get a value which now remains, let's say, reasonably unchanged as I keep increasing the volume over which I'm making this porosity estimate. So that is typically what we report as the porosity of that material. If I keep increasing the volume, and after a while, if the volume has, let's say, become of the size of the order of kilometers, then of course, if there is heterogeneity and so on, that will change. So typically, when we think of porosity, this is the region, what we call as representative elementary volume, REV, over which soil properties are being reported. And that's not true just for porosity. Same will be true for conductivity. Conductivity of just void space will be very high. Conductivity of soil particle would be zero. Unless I estimate conductivity over some representative volume, I'm not going to get a meaningful value. So that is important. It becomes important in continuum approaches at other places too, because when we derive the governing flow equations, mass conservation equation, Darcy's law, constitutive relationships, we try to do a mass balance. To get differential equations which help us understand flow, we are going to set in the limit the size of our elements, delta x, delta y, delta z are all going to zero, for the difference equations to become differential equations and become a continuum. Okay. So we'll do that, but we realize that indeed those elements are actually not ever going to zero, because if they go to zero, at the microscopic scale, the soil is way too complex to be characterized. So even though we say delta x, delta y, delta z are going to zero, we realize that in a continuum sense, we want it to be in this particular range. It's also important because if I'm taking derivatives, so if I want to take derivatives of porosity or derivatives of conductivity, for the derivative to be meaningful, I have to be in a range where this property is varying in some continuous sense. If it's fluctuating this widely, the derivatives will not be very useful. So the idea of continuum approach, or the importance of representative elementary volume, is that we want the porosities or properties, in this case I'm using porosity as an example, to start behaving in a stable manner. What is stable? Effectively means I should be able to take derivatives meaningfully. So what I would mention this because soils is not actually a continuous medium, but we are able to use continuum approximations as long as we work in the REV region, the representative elementary volume region. I want to talk briefly about surface water and groundwater interaction. It was mentioned before too that surface waters, essentially streams, they are going to react quite a lot with the subsurface, especially in the neighborhood of the stream. You may have an unconfined aquifer, and we have essentially unsaturated zones, but the stream water and the subsurface water may be under, they interacting very closely together, and one serves as a boundary for the other. So these interactions are also important to understand. If you are going to be pumping activities are going to be close to streams, then of course the stream and the aquifer being hydraulically connected, the pumping is going to influence stream levels and vice versa. We'll talk about conjunctive use of groundwater and surface water resources. It becomes very important for water rights issues. If you have farmers who are essentially have wells, or whoever has wells, and they have a certain amount of water right that they can draw, how that affects subsurface water resources and surface water resources can become difficult. And in fact, water management is actually challenged by this. Okay. Then assessment and minimization of losses and delays of water released from surface water reservoirs also becomes an important management problem. Yes. Okay. The surface and groundwater interaction, it has many facets to it. Okay. It's useful for assessment and mitigation of floods along river valleys. Floods can be very well attenuated if the water is allowed to basically go and replenish the main aquifer. Basically, and same to do with contamination. If the groundwater or surface water is contaminated, that's going to influence both flows. We basically do integration of groundwater flows and watershed management, planning and management, evaluating the impacts of riparian zones on river water quality. So basically zones that are close to the river or the river bed, what kind of activities take place in terms of exchanges of water and solutes and solute fluxes and water fluxes that has a very important role to play. The groundwater surface water interactions also control aquatic life. They support dynamic habitats, especially in wetlands and other places. So even though we tend to study surface water and groundwater as separate subjects, there are many occasions where essentially they interact quite closely with each other. I wanted to spend a few slides just quickly talking about groundwater exploration techniques, surface methods, subsurface methods, and geophysical methods. We will simply mention them. Surface methods are easy to operate and implement. You can see surface water, it's easier to access, okay, require less research work, less background information. Facilities that you are required to manage surface water are going to be easier to obtain. Subsurface methods of groundwater exploration, they basically require a much larger investment. You have to invest in digging wells, doing borehole logs, characterizing the subsurface, and so on. So the subsurface methods are the examples of direct observations. Typically, like I said, if you drill a well, you take soil cores, you essentially map the subsurface at various depths by examining the properties of the cores. And so these are physical properties, but they do require a lot more effort. And then there are geophysical methods, a separate subject sometimes, dealing with how to map the property of this Earth's surface. The part that we are, of course, interested in is in geophysics, is how they basically look at subsurface properties. And most of the geophysical methods, or many of them, essentially comprise of sending some sort of a signal, measuring the reflectance, and figuring out what the subsurface properties are going to be like. And we are able to estimate things like density, sometimes velocity, infer properties like conductivity, magnetic and electromagnetic radiative properties, all of these to try and characterize the subsurface better. But it does take a lot more effort. Within geophysical methods, we have both passive and active methods. Passive methods, like I said, they use things are happening already, that you basically use to infer what is happening, or if you have some phenomena that occur naturally, allow you to probe the subsurface a little more. Active methods are when you actually go with the intent of measuring, so you conduct field campaigns and so on, and you can use various methods to try and characterize the subsurface. So I want to stop over here to first see if you have any quick questions.
You mentioned two terms from that sustainable yield and optimal yield.
Yes. I'm not sure. So what is sustainable yield and what is optimal yield? They are in some sense synonymous. It depends on what your purpose is. So what is sustainable or what is optimal is defined by the user. So if your idea of sustainable yield is that the aquifer levels from year to year on average should remain the same, then that is a certain amount of sustainable yield. If your goal is to clean an aquifer of contamination by pumping water out, then what is sustainable or what is optimal may be dictated by different considerations. If your goal is to basically pump enough or certain amount of water so that surface waters are not going to be impacted, then that might give you a different estimate of what your sustainable or optimal yield would be. So what determines what you would call a sustainable or optimal is decided actually first by the user. You have to figure out what it is that you are trying to achieve. The idea is that we will need to use the water. We need it for drinking purposes, we need it for all purposes. Are we able to manage it? And then depending on the goal, that would define what optimal is or what sustainable. Sustainable typically means you want that resource to be available in perpetuity. So you're not going to draw more than how fast you can replenish. So sustainability usually has that definition. Optimal yield very much depends on what is your purpose. Yes.
In this videometric surface, we're talking about partially penetrating and fully penetrating.
Yeah.
If the videometric, there is no gradient of videometric surface, let us say. So then irrespective of whether it is fully penetrating or partially penetrating, the pressure will be, the total pressure will be same. All right.
The if there is no gradient,
Yes.
so there's no water movement.
Yes.
Uh,
Whether I fully penetrate the well throughout its thickness or if I just partially penetrate it.
but there is no water movement.
There is no water.
Yeah. If there is no water movement, then it's not an issue. Like I said, it's only when you have gradients, vertical gradients, if they exist, then it becomes an issue. Otherwise, it's not that much of an issue.
Can we identify the amount of subsidence due to some amount of the water extraction?
Not a very direct answer. So what is happening is the soil structure is very complex, so there's not one answer that will work. And so you have to imagine the soil as being these solid soil grains which are held together by interlocks, and then water is filling up the rest of the space. And anything that is sitting on top, let's not worry about the atmospheric pressure, but anything that is overburden pressure, whether you build a huge building or whatever, that's going to exert the load which is being borne by both soil and water. If you, let's say, remove some of the water, then the load that is being borne by the water now is transferred to the soil. And the soil then, that will have to bear the load. So basically this interlock structure, soil particles by themselves are not going to be very compressible. So because this section, there will be some slight rearrangement of the grains to basically, because you have applied the stress. And the idea is if I were to pump water back, then there would be more pressure on water, water would take more of the load, the soil would have to take less. And as long as this is in the elastic range, we are doing fine. The aquifer is in a sense able to recover. If we draw so much water out, and then depending on the nature of interconnectivity and how the interlock stresses are there, it may happen that after a while, the aquifer in some sense collapses. And that is when we have larger subsidence. We actually have subsidence in unconfined aquifers quite often, but these subsidences are typically very small. So that for most practical purposes, we are not truly worried about it. However, if we call this, when you have these large subsidences and buildings and stuff collapse, then basically after a while, something has happened that has triggered this aquifer not to be able to have that integrity anymore. It collapses. So when that happens, we don't know.
No, sir, I mean, like for modeling purpose, suppose if we are trying to some more amount of water, in the model, can we able to identify how much amount of topography substance?
Yes, we have subsidence models that account for that. Like I said, for most practical or for many practical purposes, it may not be a consideration, but yes, you can modify your equations to account for subsidence.
What are the governing equations are using that type of?
I don't have the governing equations on top of my head. I don't think in our workshop we are actually going to deal with those equations. But those equations are available in many textbooks. It's a subject that people have studied. But you can account for subsidence, yes.
I have one question. You continue approach, but what about the porous medium heterogeneity?
Yes.
The porous medium, what about the homogeneous?
Say that again, come on.
You continue approach just go the graph.
Yeah.
With this porous medium, this is the state pattern here.
Right.
This between homogeneous media something else.
So we would basically, within this averaging volume, porosity and let's say conductivity, transmissivity, other properties, as long as they are not changing, we would call that as homogeneous.
Then particles also change and
The soil what?
soil particles grain size.
We are thinking that the soil particles, the porous media as a bulk is not changing. So yes, whatever the arrangement of the soil particles is in some statistical sense, whether average, that cannot be changing. If it is changing, that means it has become heterogeneous. So you can have changing properties either because of heterogeneity or because you haven't even reached the representative volume as yet. If it is changing gradually like this because of heterogeneity, the important consideration is that change continuous or not. If it is continuous, then we are able to take derivatives. If it is not, let's say I have sandy soil immediately adjacent to this, then we have an interface. Then those derivatives, in principle, we cannot take. Then we have to model both regions separately and balance the interface so that they have the same pressure with the interface. That is the basic, the implication is that as long as these properties are continuously varying, we are able to take derivatives.
Fundamentally, how to determine effective porosity?
How to determine effective porosity?
Fundamentally.
Yeah. There are methods. You can determine total porosity if you use some means to remove all the water. Okay, you can do that. Then to determine effective porosity, I'm trying to think if I'm going to, if I'm going to do experiments with a conservative tracer that does not react with the porous medium, and if we may talk about it a little bit, if we compute what is the Darcian flux and an experimental conservative tracer, which will give me the effective velocity from which I can calculate the effective porosity, if those two are different, then I know that the effective porosity is different from the total porosity. I'm wondering if there is an easy way to do it only with flow. So, do you know of a way to get an effective porosity experimentally easily?
Voids, the percentage of voids.
Yes.
But you have to know the percentage of voids.
You can get a percentage of voids. The percentage of voids you can get. Again, the question is what is effective? What fraction of that is effective for water conduction? That might be a little more difficult. So one, I'm not sure it's easy, but one way is to have, you can determine the total porosity, and then you do an experiment with a tracer, which does not react with the porous media. That's may not be an easy experiment, but an easier experiment that will determine what the effective porosity is, because the velocity or the average velocity will be reflective of the effective porosity of the medium. Direct measurements, I'm struggling to think of. The problem is in the laboratory, we actually do not measure pore sizes, or not typically. What we measure are particle sizes. And we try to infer the pore size distribution from particle size distribution. They are not the same. That transformation is not automatic. So effective porosity is, you can determine the total porosity. You can drive out all the water, bring it in all in, and get rid of all the water from all pores. You can do that. For the same soil, if you conduct an experiment with a conservative tracer and see the breakthrough curve of the tracer, you are able to determine what the log, so you can get an assessment of what the effective porosity is, or the active porosity.
Yes, I can add something.
Yeah.
Geotechnical guys are doing a lot of, they just take this X-ray SRV techniques and they get the distribution of pore spacing and in that visual routine method in that.
If you can map the pore space very accurately, which is not an easy experiment.
But they are doing it here.
They're doing it, yes.
They are doing it. If you want to know more about it, I think you can take it from
If you can map the pore space, what's that?
Riparian.
What about it?
What is riparian?
So riparian zones are essentially the essentially that space where this surface water and subsurface water get to interact. So it can be bottom of a stream bed where the stream water is actually in contact with subsurface water, and therefore exchange of chemicals and fluxes can go on. Sometimes rivers basically, they don't stay contained within the main channel, they basically spread out to the sides of the banks, and then also lots of, so the riparian zones are essentially those zones where you have this interchange of water and chemical fluxes with both hyperwave zones. So, oh, I'm sorry, I'm confusing, I meant hyperwave zones. Right, so that was my mistake, thank you. I meant hyperwave zones. Riparian zones have to do with, again, I'm not sure what there is an exact definition, but these have to do more with agricultural applications. So that's a good point. We should change its hyperwave zone there. What we were mentioning, yes.
Riparian zones is basically what you said is from the agricultural point of view.
Yeah.
Because even in interstate issues, they come to, we have to release this much for riparian requirements.
Right.
That-
But you're right, I actually meant hyperwave zones, but it's riparian zones. Any other questions? How are we doing with time? 12:30. So will we try and continue and do the other part also, the second part? Or do you need a break?
So I have a question.
Yeah.
Actually, we study aquifer details like transmittivity, storability, these are like. So whether it is differs from block to block,
Yes.
space to this. For the study, there is also 4 blocks.
Okay.
So while collecting several block, types of aquifer details will be changed.
Yeah.
So the term on practical details. So whether which can be considered for model purpose, area practical purpose. Or else we can take the range of the values, what we should in our own, we have to mention exactly.
I'm not sure if I follow the question. If the aquifer is heterogeneous, then we model it as a heterogeneous aquifer.
Is it possible that every block it will be changed?
Yeah, we will get a chance to talk a little bit about heterogeneity, perhaps in the next homogeneity and heterogeneity, and what is actually homogeneous versus what is actually heterogeneous in the next slide. But in principle, what we call as homogeneous or what is heterogeneous is very scale dependent. So it's not a definition that you can make independently. You have to say what scale you are looking at to be able to declare something as homogeneous and heterogeneous. So we can, one thing you could do is you could wait till you talk about it and then re-ask that question. But if an aquifer is heterogeneous, then you are accounting for that heterogeneity in some way.
Using permeability only we can account the heterogeneity.
What's that?
Permeability.
Yes.
Kx is not equal to K1.
That's usually direction dependence in isotropy or in anisotropy.
One location, other location,
Yeah.
Kx1 and Kx2
Yeah.
is not equal,
Yeah.
then it is heterogeneous.
Yeah, I mean, the porosity is changing, then it's still also heterogeneous. So properties are changing in space, then it is heterogeneous. And if that is something that needs to be represented, then we would represent it as a heterogeneous aquifer. Not sure I'm answering your question.
Actually,
The four black, no, you need black transmittivity, right?
So
You should consider that, if you know the value, you should do that, right? Independent.
we will use turn transmissivity for whole activity. Permeability for unit cross-sectional area. Transmissivity for whole activity.
Transmittivity, A to B, no?
Yes, sir.
So each entity is lying in different blocks. So you consider whatever the block you are considering. You consider that why you want to take everything in house? Because the different blocks. Yeah. There's only any vehicles. We will divide that into different blocks and each block whatever the value you are getting. That is the initial part.
So we'll talk about it
Yeah.
and then ask the question again.
So actually, when collecting the depth of layers, topsoil, so these are all same. These are not same for two blocks.
Okay.
When collecting the data. But the transmissibility details will be differs.
Okay. So it's a
So we can take that difference upon that. So we can find a permittivity with that value, transmissibility value.
Yeah.
Actually, the transmissivity depends upon the thickness of the aquifer.
Yes.
Okay. Let us say if you have two aquifers which has same properties, hydraulic conductivity is same, but one is having let us say 10 meters thick and another is having 10 meters thick. If I draw water from both the aquifers with the same discharge, so in which one you will have lesser phytometric drawdowns.
So we can discuss about drawdown.
So basically, the one with more transmissivity or more thickness will give high water. Okay, so the drawdown will be less. So that's why when we build wells,
So that's why it will be same.
we will be seeing not only what is the type of material we get, but also up to what depths we have got. If I have got a little or very high depths of, let us say, sand or gravel, that means that's a very good app.
Okay.
I think it's done. So
okay. We will talk a little bit about it, I think, in the forthcoming slides. And hopefully that will clear it, but if not, ask the question again.
Yeah. I think this will be because it will be clear in the next lecture. The transmissibility is one.
Any other questions? So it's 12:30. Do we want to do the next one now so that we can go for lunch or?
Sir, actually, today
Yeah.
we will finish this lecture also,
Okay.
so that 3 o'clock, because the first tutorial is based on the second lecture,
Okay.
so that the students will have otherwise so we have to give that and again.
Okay.
And if you are
you can take one part. Yes, no problem.
I'm fine.
No. You are taking the lecture also. You need something.
Actually, I'm
They are
fine.
listening, so they don't have to take break.
I'm fairly well settled. I'm fairly well settled.
Oh,
I'm okay with.
the schedule ready? Schedule to finish.
No, we are running a little behind, I think, but let's see how fast we get, how far we get.
Schedule ready? Schedule
If you want to get up and stretch your legs, you can do that. While this is being distributed. The next section. And so we'll continue on, on this topic about we did some definitions, we talked about porosity, we talked about, we'll talk about some other properties, but let's, visit or revisit one of the classical experiments, which basically brought us the rules that we use for modeling subsurface flow. I suspect all of you have heard of Darcy or Darcy's law. And what Darcy did was conducted experiments, which are schematically shown over here. So what he observed was, in a given porous media, which has a certain cross-section area, entire bulk cross-section area is capital A, measured the flow rates and also measured the piezometric heads at the two ends. And basically what we found was that the flow rate is proportional to the difference in the piezometric heads. It's inversely proportional to the length and directly proportional to the total area of cross section. So all this combined into one basic law, which says Q equals this proportionality constant K, which we will essentially call as hydraulic conductivity. It's proportional to the area. This is the entire cross-sectional area. And then delta H is the head difference over a distance of L. So delta H over L is the rate at which, head loss is occurring, in the porous media. We call that as a hydraulic gradient. And we will assign a minus sign to it because in calculus, the derivative is taken positive if the function is increasing with distance. Here, for the flow to be positive, going from, let's say, inlet to the outlet, at the inlet the head is higher, at the outlet it's lower, so the head is actually falling for us to have positive flow, and hence the minus sign. This quantity K is what was initially called as permeability. And so Darcy's law simply says the flow rate through porous media is proportional to the head loss, inversely proportional to the length of the flow path. And so that is what we will typically use. This quantity K was and is in fact now called as hydraulic conductivity, and I want to then define something called the Darcian flux. The Darcian flux is small q, which is essentially the capital flow rate, capital Q, the entire flow crossing the cross section area A, this ratio is small q. So Q over A, so this is small q, the Darcian flux. It measures the discharge per unit area. But as we talked about, this is a porous medium, so the entire cross-section area is not all occupied by pores. Only a fraction of this area is actually involved in water conduction. And so the velocity that we would think of is some sort of an effective velocity. We are going to say A sub P is the area occupied by pores. With the pores, then if all these pores are going to be active, we basically assign something, or we call this quantity as a velocity. We'll also call that a seepage velocity later on. So this velocity is the flow discharge, but the area over which we are dividing is only the active area of the pores. Okay. And of course, so Q over A, I can basically multiply the numerator and denominator at the bottom over here with A. So Q over A is a small q. This is a Darcian flux, sometimes called as Darcy velocity also. A sub P over A is what we call as porosity, at least loosely calling it as porosity. So the Darcy flux, Darcy flux and Darcy velocity are terms that are interchanged. V sub S is termed as seepage velocity, and since porosity is obviously less than 1, the seepage velocity, sometimes called as effective velocity, is going to be greater than this Darcian flux. The confusion, there is a lot of confusion occurs because specificity has units of length over time. This is meter cube per second divided by meter square. V sub S, the seepage velocity, also has units of length over time. And hydraulic conductivity also has units of length over time. They're not all the same quantities. Just that, they're not all velocities in some sense. Conductivity is a property of the medium. Nothing is moving for us to define a conductivity, but it has units of length over time. So we need to be careful, and that care becomes more relevant if we are talking about contaminant transport. Some definitions. Darcy's law, when we talk about typical groundwater flows, was expressed in this particular form. This is expressing in terms the head loss that the water is experiencing as it moves through the porous media is because of friction through the pores. And just as we recall from pipe friction and other considerations, how much head loss we get does depend on the flow velocity, or in this case, the Darcian flux small q. Darcy's law, for it to be applicable the way we know it, the flow has to be very slow, well within the laminar region. And typical velocities are very small. If the velocity tends to be high, then the head loss is not just proportional to Q, but Q raised to some certain power. That means we will have more head loss than we expect from Darcy's law. And so to think of validity of Darcy's law, just as we do in pipe flows, we use the Reynolds number. Reynolds number is, is given over here. So we have mu over rho, which is the kinematic viscosity. There is a velocity that we have to use. And then Reynolds number has a characteristic length. When we do pipe friction kinds of things, then velocity is the average velocity of water in the pipe. The characteristic length over there is the diameter of the pipe. And in porous media, what is going to be that characteristic length typically is equated to the particle size diameters. And so D10, so that gives you a size of the particle sizes. That is typically used to characterize a Reynolds number for flow, in porous media. But porous media flows are very, very small or very small velocities, so that, most of the time we think of it as being obeying Darcy's law. If the velocities tend to be very high, that means the gradients are very sharp, then Darcy's law is going to be violated, then you might have to make some adjustments for it. Okay. So very close to the wells, the streamlines become very steep. You have to account for that somehow. So Darcy's law, since groundwater velocities are such, very small, Reynolds number less than 1, and most of the time we are in this range. There will be some exceptions. Like I said, flowing close to a well, as the water approaches the well, the streamlines are going to be very curved. The piezometric surface is very steep. But for most applications, we do fairly well with Darcy's law. We often see the term permeability. Permeability is sometimes different from conductivity depending on which sub-area you are from. So soils, people think of permeability as perhaps what we would call as intrinsic permeability. Also comes from similar constitutive relationships like Darcy's law, where the flux is proportional to a gradient and length. We have in electrical circuits through Ohm's law and conductivity, or Fourier's law when we do heat conduction. Initially, it was thought that this conductivity is a property of the medium, and it would be if the fluid was always water, and if the fluid properties were not going to change with things like temperature. But otherwise, it does depend on the media and the fluid, on the porous media and the fluid. Okay? So conductivity is proportional to gamma, inversely proportional to viscosity, and so on. So what we typically call as hydraulic conductivity K is small k, which is the intrinsic permeability of the medium. So this is property of the medium. It basically depends on the nature of the pore spaces, the nature of the soil, and so on. Whereas fluid properties are essentially encapsulated by gamma over mu, specific weight over viscosity. And this product is what we call as a hydraulic conductivity. Hydraulic meaning the fluid is water. Water, for typical temperatures, the specific weight doesn't change much. Viscosity does change, but in groundwater concentrations, most of the time the temperature fluctuations are not that high. So we think of the hydraulic conductivity. If the fluid properties do change, then of course the conductivity will change as well. You will need to worry about properties changing, as was talked about earlier, if we talk about saltwater intrusion in coastal aquifers. So if salt water is mixed in the water, its density will be significantly different. And so some of its properties are different. If your fluid is not water, if it's any other contaminant, or if it's petroleum or some other fluid, then of course gamma and mu will change. I want to talk a little bit about isotropy and anisotropy. In fact, came up in the earlier questions. The hydraulic conductivity is a property that is directionally dependent. And in fact, it's more of a tensor. But this idea that we are talking about flow in a particular direction, we're applying the gradient and measuring the flow in that direction. If that direction happens to be x, we would call that as k sub x. And similarly, again, if you have other orthogonal directions, y and z, you would have k sub x, k sub y, k sub z. So hydraulic conductivity, if these properties, k sub x, k sub y, k sub z, are all same, in other words, in different directions, conductivity is the same, we typically call that an isotropic porous medium. Anisotropic would obviously mean that k sub x, k sub y, k sub z are not all the same. Okay. What creates isotropy or anisotropy? Well, fundamentally, like I said, we'll see. Fundamentally, however, it depends on how aquifers were formed, how the layering. Most aquifers essentially were built up in layers. So the fact that you already have layers means that you will have anisotropy. But that is the fundamental origin of anisotropy. But anisotropy comes from other considerations as well. However, depending on what we are trying to do, what we are trying to solve, what we are trying to model, that determines this. And if we are able to put our properties are not changing in direction, then we would say isotropic, otherwise it's anisotropic. And we'll look at some very simple ideas of anisotropy, which we are able to motivate through layered soils, okay, which you have perhaps all seen. So here we have an example of, let's say, a soil which has different layers. And each layer has a different thickness, D1, D2, D3, D4, however many layers you have. And each of these layers has one conductivity. And for now, we will assume that these layers have been deformed. They are thin enough that within each of these stratifications, each of these layers, the conductivity doesn't change the direction. So if this is my horizontal direction, this is my vertical direction, for the first topmost layer, K1 is the same whether it's in the X direction or in the Z direction. At least let's assume it's so. Similarly for D2, D3, and D4. Now, if I'm applying Darcy's law throughout this, throughout this porous medium with all these layers in the horizontal direction, in the X direction, I'm measuring the piezometric head of water throughout the thickness at a certain location here. At some distance, delta L away, delta Lx away, I'm measuring the piezometric head. There is a fall in piezometric head, that means water is moving, in this case from left to right, but it's moving through all the layers. So this is a case where we have flow which is parallel to the stratification, parallel to the layers. Right? And I'm trying to figure out what I can say about the flow in this particular scenario. So while we do have K1, K2, K3, K4, and so on, and water is, let's say, essentially moving in the horizontal direction, what I would like to do is assign one single effective hydraulic conductivity in the horizontal direction, which will describe bulk movement of flow throughout the thickness of this aquifer, throughout all those layers. Okay. So if basically I think of this particular picture perpendicular to the plane of the picture, let's say it's unit thickness, and this total thickness is D, then the flow is occurring through a thickness of D times 1 unit. Now, if the flow is occurring in parallel through all these, all the layers over at this location are seeing the same piezometric head. All the layers over here are also seeing the same piezometric head. So the flow through each of these layers is responding to the same gradient delta H, or same head difference delta H, or a gradient of delta H over L. And therefore the flow through the first layer is this gradient times the conductivity to the first layer times the thickness of the first layer and multiplied by unity perpendicular to the screen or perpendicular to the picture. Total flow then, if the flow in each layer is Q sub I, the total flow is going to be simply the sum of all the flows, and that will give me the flow through all the thickness of the aquifer. If I want to think of an effective K sub S, I want to basically apply Darcy's law throughout the thickness of the aquifer. Delta H and this are the same. I have to say there is one effective K that should be equal to the gradient delta H over L times the area, which is sum of all these individual thicknesses times the 1 unit perpendicular to the perpendicular to this picture. And basically I equate both these flow rates to find that my effective conductivity, K sub X, horizontal conductivity, is given by this expression. So K sub I di divided by small d, where small d is the sum of all the individual thicknesses. So that gives me K sub X. So in other words, if I were to write Darcy's law for this whole block for flow in the horizontal direction, I would use K sub x as my effective conductivity. So while the aquifer is indeed, or it is indeed heterogeneous, properties are changing with depth, if I want to replace them with one effective value, that's what I should do. I can ask the same question and say, what if I wanted to replace, or what if I were interested in flow perpendicular to the stratification? What should be my effective one single K value? If the flow is essentially going perpendicular to the stratification, the positive Z direction, you would essentially apply the same principles. Now, assuming that it's steady state, there are no storage effects, we know that whatever Q, whatever the flux is that is passing the first layer or the bottom layer must pass through the other layers as well. So that Q basically then remains constant. But over this distance delta L, the head loss for water in the first layer, in the second layer, and third layer could all be different. So we again apply Darcy's law basically. And we say that, well, if delta HI is the head loss or the difference in heads in the first layer, that will determine the flow, that is going through that layer per unit cross section area. It will also be, the head loss will be determined by both the thickness and the hydraulic conductivity of stone. So again, Darcy's law, but applied in the vertical direction. And then so basically the flow is now the same in all these layers, in all these stratified layers, but the head loss in each is different, and that will depend on the K for that layer, the thickness for that layer, and of course the Q that's going through all the layers, but that Q is the same. So we can again do the same thing. Find out what is the head loss to each of these layers. The total head loss that this is experiencing as a block then is sum of all the head losses to these layers which are in series. And then we can again equate these two total flows to find that the effective K then that I should apply in the Z direction is given by this particular expression. So D is again sum of all the DIs, but now on the denominator I have DI over KI, and I'm summing all of those up. So for the same porous media configuration, because it's stratified, in the previous slide, says the effective conductivity in the X direction is given by this expression. So it's one averaged K value, but its averaging process is different. If it's going perpendicular to the stratification, we again get an average K value, but the process of averaging is different. And it can be shown that when we do this, K sub X and K sub Z with these expressions, K sub X will always be greater than K sub Z. To flow parallel to the stratification, to move water parallel to the stratification is far easier. The conductivity is higher, so with a smaller head loss, you can move the same amount of flow. So an isotropic ratio sometimes talks about the difference between K sub X and K sub Z, function of layers, and that this ratio can be small or high. It will depend on the nature of the porous medium. So this idea of isotropy and homogeneity, heterogeneity, these are all tend to be very scale dependent. But any questions over here? Okay, so let's see if we can try and answer this question that you had before. If I consider 3-layer aquifer, you can see this is the top layer, this is the bottom layer, and this is the middle layer, this is the bottom layer. So in these 3 layers, within each layer, let's say the aquifer is individually homogeneous and isotropic. So as long as I'm in the top layer, K sub X and K sub Y are the same, and not only are they the same, they are not changing the location also. So it's homogeneous. If I'm in the middle layer, same thing. It's homogeneous and it's isotropic within itself. But of course, from layer to layer, these properties are changing. So now let's say I want to model this kind of a porous medium, and I impose a finite element or whatever grid I want. And let's say this is my finite element grid. And what I'm required to do now for my model of finite element is provide a property in each of these elements. So when I do that, you notice that each of these elements is within that same medium. So I treat this as if within where I'm providing this particular property over here, this is an isotropic medium. I go to any element, case of x and case of y, or case of x and case of z are the same. However, depending on whether my element is here or somewhere else, I would have different properties. So I would basically model this as an isotropic but non-homogeneous. Let's say I take the same aquifer. However, my block that you're talking about or my element size is given by this. And I have these as my element size. So if I have to prescribe one property for each element now, because I have these three in layers, case of x would be essentially parallel to the stratification. Case of z would be perpendicular to the stratification. Those two values will be different. So when I go from element to element now, it's anisotropic, because case of x that I have to assign to this element versus case of z are going to be different. Case of x is going to be more than case of z. But as I go from one element to the other, case of x values are the same. Case of z values are also the same. So I think of this aquifer now as homogeneous but anisotropic. So this is what I was trying to indicate. The question of whether something is homogeneous or heterogeneous, whether something is isotropic or anisotropic, depends on which scale you are looking at. The same aquifer in this particular configuration was non-homogeneous but isotropic. But in this configuration, instead of being non-homogeneous has become homogeneous, instead of being isotropic has become anisotropic. So the question is, whether it's homogeneous or non-homogeneous depends on what your application is. You cannot beforehand declare something as homogeneous or isotropic. And so that is, so isotropy and homogeneity are also governed by the application time. So this is also leading to your question. You were saying, if I'm using this as my block size, I'm going from one block to the other block to the other block, nothing is homogeneous, but it's not isotropic. Whereas in this case, it's isotropic at any given location. The properties are same in all directions, but from location to location, properties are changing. Okay. So we'll briefly go through this idea then. If we have flow in multiple dimensions, then of course, flow processes can become more complicated. If I'm thinking of the XZ plane, for instance, as we were looking at in the previous example, then the Darcian flux, small q sub x or q sub z, how much flux goes in the x direction, depending on the nature of anisotropy, it will depend both on the conductivity along the x and along the z directions. So K actually becomes a tensor. If it's a three-dimensional porous medium, if you're doing analysis in 3 dimensions, then you have a 6, or you have a larger tensor, 3 by 3. And if the elements are symmetric, it means Kxy and Kyx are the same, then to basically estimate the hydraulic conductivity, you are trying to estimate 6 individual parameters. It becomes complicated. And, so for most applications, we assume that the porous medium is aligned in such a way that our axis x, y, and z correspond to what are called as principal permeability directions. Then the cross terms determine, and we are still left with trying to estimate case of xx, case of yy, and case of zz.
What are the assumptions behind this? By neglecting the cross terms,
Yeah.
what are the assumptions they have been considered?
Well, I think that is a very difficult question to answer. The assumption is you're assuming that you have chosen the x, y, and z directions by knowing the nature of stratification. The implications of what happens if that is not the case, because x, y, and z we choose, let's say, arbitrary, and let's say the layering is not along the principal directions, that is actually a very complex question. At least it's complex in the sense that when we do, trying to do my spiel, when we model things, when we do modeling, groundwater flow equations, and so on, these properties, well, conductivity is different enough, and transmissivity are not independently available to us. We use something called calibration. And calibration is what we call is going to compensate for the fact that our choice of axis may not be aligned with the principal axis of the medium. I'm not sure that's the correct answer, but the answer is yes, there's a difference. But exactly what that difference is usually gets buried in everything else that calibration does.
Can I answer it?
Yeah, go ahead.
No class component, no.
What happens if you take any arbitrary direction? V is equals to k to x, k to I, or 6 bar. See, if you have an entropy k, okay, and I is also, if you are taking a different direction, the resultant V will not be in the direction of I. It will be deviate from I. So, but we know that the flow will take only along the direction of gradient. So the cross component will have to make.
Yes, the answer here, no, there are no
The
class.
tensor notation.
Yeah.
Once if I choose the directions as the principal directions, those cross components will go.
Simple to understand, kx, ky.
When the tensor will become all the cross components of the tensor.
Okay. So for 2D horizontal flow, we talk about the idea of a transmissivity. So same idea, if this is flow, capital Q x prime is the flow throughout the thickness of the aquifer in the x direction. Capital Q y prime is the flow throughout the thickness of the aquifer, but in the y direction. So we are not worried about, let's say, flow components in the z direction. And there are, you can talk about when that could be neglected and when that's important. But if flow is essentially two-dimensional, then instead of conductivity, we use transmissivity, which is a property of the aquifer, because now we are talking about how much flow is occurring throughout the thickness of the aquifer. So this transmissivity is encompassing all the heterogeneity or stratification, all that you have in the z direction. So again, it will be a tensor, but same rules will apply. Even the 2D field, it's a matter of whether it's aligned along the principal directions or not. The x, y, and y x, if they can be, if they can be ignored or compensated for, then you'll have two principal directions to worry about, txx or two parameters to worry about. So transmissivity gives us the same idea or the same information as conductivity, but now it's throughout the thickness of the aquifer. And then the flow here is throughout the thickness of the aquifer in the horizontal direction. And for many applications, we are indeed interested in flow throughout the thickness of the aquifer. So that is transmissivity. It is responding to changes in piezometric head, H. And so the H, the piezometric surface, is now a function of X and Y. So transmission, and so we talk about aquifer parameters. We have been talking about transmission, which talks about movement of water. So we'll talk about storage properties later. Transmission, it derives, basically talks about flow properties. So now it's transmissivity is something that we identify as an aquifer property. It's not just a property of the medium. It depends on the thickness, it depends on stratification. All of that is included in my definition of transmissivity. And transmissivity in the x direction, this is my horizontal x direction, throughout the thickness, I'm looking at conductivity in the x direction, but it could be varying with z and integrating all those effects. So I have conductivity in the x direction multiplied by the thickness. So this case of xx in some sense would be the effective conductivity throughout the thickness in the x direction. Similarly, case of yy would be the conductivity in the y direction, but multiplied by the thickness. So transmissivity would have units of meters per day, because it's like conductivity, length over time multiplied by length. In an unconfined aquifer, transmissivity is a little usually unclear, because in a confined aquifer, the top and the bottom of the aquifer are determined. They do not depend on the flow. It's always confined. The piezometric head is not affected by the thickness of the aquifer. In an unconfined aquifer, when we talk about flow throughout the thickness of the aquifer, the thickness of the aquifer that is actually going to be involved in conduction does depend on the piezometric head, H, the height of the water table. And so therefore that basically brings in this complication that the description of transmissivity would depend on the height of the piezometric head, whereas for a confined aquifer, that was not the case. And of course, for water to move, there has to be a change in piezometric head, but the change in piezometric head for an unconfined aquifer would imply that the water table is falling, or it's not constant. And so therefore that also brings in the extra consideration that when you define transmissivity, conductivity throughout the thickness of the aquifer through which flow is occurring, you have to contend with the fact that that quantity could be changing. So unlike a confined aquifer where it's a separate property, does not depend on the piezometric head, in unconfined aquifers it does. However, if the water table fluctuation, let's say with time, is going to be small compared to the thickness of the aquifer, then we can think of this water table fluctuation as water table changes as small fluctuations about some, let's say, average value. And then we can then still assign a transmissivity, which is this average thickness of the aquifer times the hydraulic conductivity. And that is what is sort of indicated over here, that we may be able to, if these fluctuations of the water table height are small compared to the thickness of the aquifer, so there is a mean hydraulic head, a mean piezometric head, that is H, changes are small, then we are still able to basically describe an average H bar, an average height at any given location, and talk about a transmissivity. But you have to realize that the transmissivity is now going to be depending on H. Okay. If we assume mostly horizontal flow, which requires us to do something called Dupuy assumption, then of course we are able to replicate what we see to some extent in a confined aquifer, this idea of transmissivity for unconfined aquifers. The Dupuy assumption essentially says that for water to move in an unconfined aquifer, the water table height has to keep changing. But we hope that this change is not very rapid. Now this is change in space. So what we are saying is the gradient of flow that is causing water to move from one location to the other is actually this change in height in the water table. That is the delta H. So at the bottom, the streamlines are essentially horizontal, but as you come close to the surface, since the water table surface is also a streamline, they're getting curved. So that does give a slight problem. So at the top over here for the water table, to have this particular gradient, it's traveling through this curved path, which is slightly longer than the straight path. And for us to be able to apply Darcy's law very easily, we would like to think, at this location, I have a certain piezometric head, at this location, I have a certain piezometric head. Flow is essentially horizontal, but is driven by this difference in piezometric head. So we would like to make that approximation, and that's what Dupuy allows us to do. What it essentially says is when we are coming close to the top of the water table, the distance through which water has to travel is actually not the horizontal distance, but a curved distance. However, if this angle over here is small, then we basically say that this curved distance over here, delta S, is almost equal to delta X. And therefore, I can assume essentially horizontal flow, treat the piezometric head over here as one value, piezometric head somewhere further as another value, and use this gradient to drive the flow. And then, as flow is moving at any location, I then think of this as my transmissivity. But it is dependent on the piezometric head. So that is Dupuy's assumption. It says, allows us to assume that at any section, the streamlines are all essentially horizontal. So we make some error close to the water table, but usually that is a small error. So the transmissivity and conductivity are aquifer parameters for conduction. Let's quickly talk about storage parameters because you need those for the tutorial today. Storage parameters obviously reflect the ability of the medium to absorb or release water. and we are interested in how much water is going to be absorbed or released if the piezometric head changes, because we think the piezometric gradient is what is pushing water. We define something called specific storage, and by definition, it is going to be the volume of water that is released from a unit bulk volume of the soil or unit volume of the porous medium per unit decline in piezometric head. So this is a medium property. So it's volume of water divided by bulk volume of soil. So that is volume over volume per unit decline in piezometric head. So it has dimensions of 1 over length. So at different heights of at different locations, if I choose a unit volume, if I can figure out somehow how much volume of water is released when the piezometric head at that location goes down by a unit amount, that will give me specific storage. For most aquifers, when they are dealing with essentially horizontal flow, we are thinking of flow going throughout the thickness of the aquifer. Dupuy assumption, and essentially horizontal flow assumption. We are looking at piezometric head at one location, piezometric head at another location. We are interested in knowing throughout the thickness of the aquifer, how much water am I releasing when, let's say, the water table height falls from one location to the other. If there is a unit decline in water table height, for an unconfined aquifer, that's a unit decline in piezometric head. For a confined aquifer, if there is a unit decline in the piezometric head, I want to know how much water is coming out throughout the thickness of the aquifer per unit area of the aquifer. So now we are interested in aquifer level properties. So how much storage of water is there? If the water table falls a certain height, how much water is essentially coming out of the aquifer? If the piezometric surface falls by a certain amount, how much water is coming out throughout the thickness of the aquifer, but per unit area in the x and y directions? Those are aquifer properties. If the aquifer is all homogeneous and so on, you can think specific storageivity was per unit volume. If I were to multiply that by the thickness of the aquifer, and that would give me how much water is coming out throughout the thickness of the aquifer. So that is what we call a storage coefficient, sometimes also called as storageivity. So it's volume of water released for a confined aquifer. The piezometric surface is dropping. So volume of water released from unit area of the aquifer per unit decline in piezometric head. So volume divided by area divided by unit decline in piezometric head. So storage coefficient S is dimensionless. For unconfined aquifer, it's the same thing, but now it's a fall in the piezometric surface, which actually means a fall in the water table. So we then use the term specific yield for unconfined aquifers. A definition is volume of water that is, I'm going to say, ultimately released from unit area of the aquifer per unit decline in piezometric head, which is in this case per unit decline in height of the water table. And I say ultimately because this release of water as the water table falls may not be instantaneously available. It might take certain time, so a certain time lag for this full specific yield to be realized. Sometimes you can neglect that, and sometimes you may want to take that into account. S sub y, water coming out of an unconfined aquifer, tends to be much higher than for a confined aquifer. So it's easier to develop an unconfined aquifer and pull water out of it. Because S sub y, the water that's coming out of storage, is basically, obviously, the water table has fallen through certain levels. So the pore space that was initially all occupied by water, some of that water is what we're able to pull out. So it's fairly easy to get that. However, for a confined aquifer, in principle, the top and the bottom of the aquifers are still the same. It was saturated before, it is still saturated now. So the water that we are putting out is coming because of compressibility effects of water and of the porous medium. Water in this instance, compared to solid soil particles, has some compressibility, but water is also still fairly incompressible. Not easy to pull water out because of compressibility effects. So for the same energy that you expend, which is given by the fall of the piezometric head, the amount of water that you get from unconfined aquifers will essentially be much higher. Or in this case, if you want the same volumes, the amount of drawdown that you are going to get in an unconfined aquifer is going to be smaller than what it is in a confined aquifer. A lot more energy has to be expended to remove the same amount of water. Okay, I'll stop over here and see if you have any questions.
When we are doing modeling,
Yes.
we on the experiments also we will be knowing the horizontal perpendicularity K,
Yes.
but not K judged we cannot measure. How to measure K for determining the anisotropy? How to measure the K judged?
How are you measuring the horizontal conductivity in the field?
Not in the field, the laboratory, constant head and variable head.
So, I mean, the thing is, if you have the soil, if you have a vertical core, you bring it to the experiment, you are getting vertical conductivity. If you do the horizontal core, bring it to the lab, you are getting the horizontal conductivity. So, if you are bringing it to the lab, then the experiment doesn't change. It's just a matter of which way the core was oriented. So, the same method that you would use for the method then, if it's soil core that's coming to the lab, then the method remains the same. It's a matter of how the core was oriented in the field, and you're getting conductivity in that direction.
What do you mean in the validity of Torcilla? Why we are considering the characteristic length as D10?
Actually, what is characteristic length is a matter of what the problem is. So we could almost ask, why is characteristic length going to be something? So the way characteristic lengths are defined in dimensionless numbers really depend on the problem and what is the length scale that is affecting the fluid. So actually we use D10 or D90 or D50 simply because they're easy to measure. Particle size diameters we're able to get fairly easily. Pore sizes are much more difficult unless you do some very expensive measurement. Right? So basically what the expectation is the pore size is going to be dependent on the particle size. And so that's how the D10, I think, the soil size diameter was empirically decided, let's use this to determine the Reynolds number.
In the leaky confined lab, the water is coming from down to up. Due to the pressure difference, something, physiometric difference.
Yes. So in the leaky aquifer, whether the water is entering the aquifer or leaving the aquifer will depend on what is the piezometric head inside the main aquifer and what is the piezometric head on the other side of the boundary. So it could be water coming in or water leaving, but this difference is going to drive flow in that direction. So the direction of the leakage is not, it will depend on what the conditions are. Any question? If you do have questions, remember there is a session later on. We're certainly able to bring those questions, but hopefully you'll have some problems for you to look at. But promote the hurry if you want to announce about that.
Yeah, we can meet 3 o'clock or 3 to 5, and we will do the tea break also. So during that time, we have to go through the some problem and get some discussion also. Okay.
Yeah.
First tutorial, the first afternoon session, the problems will be what we have discussed. Okay, this specific storage problem.
One thing I want to know is, do they all need to bring their calculators and laptops?
Yeah, anything is calculators. Calculators are enough. If you have laptops, that's fine. But calculators are enough.
I think calculators are enough for today, but I'm not sure about what tutorials are later. But either way,
We start giving now. I will already.
What sir is telling is for the next time we need laptops for. I don't think.
okay, all right. But you might need a calculator, please. Okay, thank you. All right, we'll see you later in the afternoon.
It's 2 o'clock.